All right, everybody, this is Mr. Krowski. Hope everybody's doing okay. What we're going to do now is take a look at really an introduction to chemistry here, our first unit, which is basically about matter and classifying matter. So we're going to take a look at the states of matter first today. And if you could look at the picture on the screen here, you can see that there's clearly a table with a bunch of stuff on it, and some people analyzing that table with what looks like our magnifying glasses. And what the image is trying to show us here is that the stuff on the table is actually made up of smaller stuff, right? Smaller pieces. And what we're going to do is take a look at those as we progress through the course and see how all that works. So chemistry really is the study of matter. Well, we're going to define what matter is in a little bit, and you probably know it from a previous science class already. But it's the study of matter and how matter changes, the changes that matter undergoes, which will be a lesson later on in this unit, an introduction to that. So let's get started and take a look at a simple question here, which is which of the following are examples of matter? So rock, water, carbon dioxide, only 1 and 2, or all 3 of those. So think about it for a second. You probably have a guess in mind. Most students definitely will say number 1 is a definite state of matter, piece of matter, and number 2, and then sometimes it's a mix on number 3. So what I have here are rock is a solid, water is a liquid, and carbon dioxide is a gas, right? So usually solids and liquids, students say, yeah, no problem, they're matter. But gases, that's where it gets a little bit like wishy-washy there. Some say gases are matter, some say they are not. So if you answered how you answered in that question, if you picked all 3 or just the first 2, what criteria did you use to pick your answer? So if you knew that certain items in that list were matter, you had to come up with an idea of why. Like, why was that matter? Why do you consider that matter and some not? Or all 3 of them, why do you consider those matter? So there's really 2 criteria that something must meet in order for it to be classified as matter. Okay, so matter is anything that has mass and takes up space. So mass is one of our criteria, and takes up space, we have a fancy word for that, which we'll define in a little bit. But you might know what it is, but it's volume, right? So volume is the amount of space something takes up. So it takes up space is really just, it has volume. So matter is anything that has mass and volume. Okay, so obviously when we looked at that list before, a rock has mass and it takes up space. Easy. The liquid that was there has mass, takes up space. Right? We can see that. But gases are a little tricky because do they take up space? Do they have volume? Well, the answer to that question is yes, right? If you blow up a balloon, it's full of gas, which is mostly carbon dioxide from you exhaling into the balloon, which is what that gas was on the previous slide. So yeah, it takes up space, it has volume. But does it have mass? That's the part that tricks students up a little bit. So we could take a look at some different gases and see if they have mass or not. But one of them that I like to look at is helium. So, if you blow up a balloon with helium, you let go of it, the balloon floats, right? So students think, oh, it floats, so it doesn't have mass. Well, there's a short little video clip here to see if that's correct or not. So let's take a look at that, and then we will go from there.
Hi. No, I'm not having a party. And no, I'm not about to make balloon animals either. I'm just filling this balloon up with helium. Want to know why? I'll show you why. Here's why. So does that mean that helium has no mass? That it weighs nothing? Okay, the tank with the helium in it weighs 6.030 kilograms. Now, if the helium weighs nothing, then letting it out of the tank should make no difference, right? 6.027 kilograms. That's 3 grams less. Well, what do you know? The helium does have weight, which means it must have mass. But if it has mass, then why does this balloon go up?
Okay, so you can clearly see from that clip there that helium, which is a gas, does have mass. And the question at the end, why does it float? That has to do with density and how tightly packed that gas is compared to the air around it. And we'll talk about density and all that in a later unit and more in our measurement math unit. Okay? So you can see that the mass went down from 6.030 kilograms to 6.027 kilograms. So that little bit that he let out clearly had some mass. So it takes up space, it has mass, so gases are matter. If you answered that correctly on the previous slide with our solid, liquid, and gas, then congratulations on that. So how many phases of matter actually exist? 1, 2, 3, 4, or 5? Most students at least say 3. Okay. Some students say 4 because they know of another state of matter. But in reality, the answer is actually 5. And there might actually be like more now if you Google it and look it up. But we have 5 main states of matter. Really 3 that we're going to study and be really familiar with. 2 other ones that are kind of cool to talk about, and there might be some other like newer weird ones that are out there. But the official answer here for now is 5. So what are they? Solid, liquid, gas. We know that already, right? The 4th state of matter, if anybody has heard of this, it is plasma. This isn't the plasma like in your blood you might have learned about in biology. This is a variation of the gas state of matter, which we'll look at in the next slide or two. And then the last one is something called a BEC, or a Bose-Einstein condensate. So a solid, liquid, gas, we're familiar with those. Plasma is when a gas gets really, 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 really hot. Okay? Think of the stars or the sun, right? And the gas is, something happens to the gas when it gets really hot. We'll look at it in a second. And the Bose-Einstein condensate, I want you to think of that as like the opposite of plasma. Something that's really, 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 really cold, okay? Just barely above 0 Kelvin, which is like the lowest temperature we can have, okay? So particles tend to act a little bit differently when you get really, really, really low in temperature, close to absolute 0. And that's what the Bose-Einstein condensate actually is. So it's pretty neat. So plasma is actually the most abundant state of matter in the universe, because it's in stars, which, you know, our sun is a star, right? So if you think of all the stars that are in the universe, well, that's an awful lot of plasma, right? And then there's some that are, you know, here on Earth, right? You have some neon signs, you have plasma TVs, our fancy light bulbs, right? So certain lighting has plasma as its state of matter. Not a lot of it, though. You don't need a lot of it to make those items. So plasma is an ionized gas. We don't know what an ion is yet because we haven't, you know, it's our first lesson in the whole course. But you can make an ion if you take away or add electrons to an atom. So if a gas gets really, really like hot, you have a lot of high energy and pressure, you can actually strip electrons from the gas and turn them into ions. So that's what plasma is. It's an ionized gas. It's the simple version of what we're going at here. Since plasma is just a charged gas particle, like an ionized gas particle, we can say it acts closest to a gas. So what state of matter is plasma close, like, you know, most like? It's the gas state. Okay? And Bose-Einstein condensate on the opposite end of the spectrum is more like a solid. Okay? So no other properties are similar, it has other properties that are similar to gases, no definite shape, and no definite volume, which we will get to in just a second. Okay, so that's plasma. Okay, so let's take a look at the 3 main states of matter, solid, liquid, and gas. And we're going to look at observable properties first. So an observable property is if you have a hunk of solid on your desk and you look at it, what can you observe? So I get students telling me a lot about like different particles and how the particles move. Well, you can't really see that, right? If you had like a Lego structure on your desk, you can't see the particles of the Lego moving, right? What could you observe about that solid particle, like that Lego structure on your desk? Well, you could really only observe a couple things. You could observe that that Lego structure has a definite shape. Okay, the shape isn't changing before your eyes, right? The Lego structure is what it is. And it's definitely not changing in size, right? The volume or the amount of space that Lego structure takes up is the same. Okay, so it has a definite shape and a definite volume. You can't really observe anything else other than that. So I have a picture of a, it looks like a solid, like block of salt here. And you can see that, all right, definite shape, it is what it is, and it's not changing size, the definite volume. Now, take a look at liquid. If you had a glass of water on your desk, what can you observe about that? Again, don't think of particles and how they're moving. We'll get to that. Just look at what your observable properties are. It's really the same as a solid for one component, and it's different in terms of another component. So liquids do not have a definite shape. If you bump that glass, of water, the liquid inside would move around, right? If you poured it from one glass to another, that maybe is a different size or shape, then you would see that the shape of the liquid changes, right? If you spilled it all over your desk and the floor, clearly the shape has changed. So liquids do not have a definite shape. They take the shape of their container, but they do have a definite volume. If you had 3 cups of water in that container and you spilled it, well, now you spilled 3 cups of water on the floor, right? So you have 3 cups no matter what. That volume is definite. So solids have definite shape and definite volume. Liquids have a definite volume but no definite shape. And then finally, we go to gases. Okay, I have here liquids can't be compressed. We'll get to that compression when we talk about gases here in a second. So what can you observe with a gas? You can observe a lot more. Okay, so gases take up space. Clearly, if you blow up a balloon, you know the gas is inside that balloon. And we know from that video that we saw, that clip a few minutes ago, that gases have mass, right? We saw that the helium gas, like that tank of it, lost mass when some of the helium was let out. Gases do not have a definite shape. They also take the shape of their container. So if you could somehow have a bunch of different like glass containers and you could seal them all off, they're all different like shapes and sizes, you can transfer one gas like to the next container, to the next container, to the next container, and you'll see that like the gas would take the shape of either one, right? Because gas particles are always moving around and expanding, and we'll see that in a little bit. They also do not have a definite volume. So basically they're the total opposite of solids, right? Solids have a definite shape and definite volume. Gases do not have a definite shape and they do not have a definite volume. Because they can expand or they can be compressed. Okay, solids and liquids, maybe a tiny, tiny, tiny bit, they could expand or be compressed, but not very much. That's what I have right here. Okay, and gases, if you had a colored gas like chlorine, which is a greenish yellow gas, and if you did see that, I wouldn't really stand around and observe it that long because that's poisonous and you don't want to breathe that in. But if you had that, or if you dyed a gas a certain color, you would see that it diffuses rapidly. So diffusion is the movement of one substance through another. So you can see my image down here. You can see here 2 gases. You know, this pink or red one here, you've introduced that gas into a room or a system, and after a little bit of time, it diffuses. It goes from an area of high concentration, a lot of that pink gas right here, to an area of low concentration. So there's not a lot of it elsewhere, so it spreads out and takes up that amount of space. Okay, so that's your kind of your expansion or movement of that gas that we call that diffusion. Now, we could look at a simulation here, and we could observe like the nanoscopic level here of solids, liquids, and gases. We could really like zoom in and see what the particles are doing. And that's what's really neat, and that's what's really important to understand when we're studying these, you know, how those particles actually interact and move around each other. So you can go to a certain website, maybe I'll put it in the description here, to kind of play around with that a little bit. You could also take a look at the slides here, and I kind of took some animations of what you would look at, and we could look at those. So if we're zooming in here and we're looking at the kinetic molecular theory for solids, so kinetic means what? Well, kinetic means movement, molecular, molecules, and theory, like our idea of how these things operate. And we can't actually zoom in like in real life and see an individual small particle like with this much detail, right? But we can do some experiments, and we could look at, we can make some observations and kind of make a prediction about what the particles would do and what they would look like. That's what this is. So it's our kinetic molecular theory of solids, and we're going to use this animation here to make some more observations. So we can't see these with our eyes naturally, so we have to use an animation to zoom in and look at that. So some of this is the same as what we had earlier for an observation, and some of it's different. You can see that the particles here are packed tightly together. Okay, so there's definitely not a lot of space between them compared to some of the other states of matter that we are going to look at. Clearly organized, right? Typically, I put that word there on purpose, typically very dense. Solid particles are typically very close together and more like closer together than other states of matter would be. This is the same as before, definite shape and definite volume. And the particles don't move much, but they do vibrate in place. So what students will think often is they're like, oh, well, the particles aren't going to move at all. And the particles like stay in place with no movement whatsoever. And that's not true. Okay, the particles do move a little bit, but they don't like move like all over the place here. They just vibrate in one location. You can kind of see that occurring here on the screen. Solid particles, they do have different like stretching that occurs. You can see some of the different stretching here on the screen. Kind of a funny animation here, what some of the molecules will do. They all have different like names and stuff, so you could check those out and maybe get a laugh out of some of them. But anyway, that's really it for solids there. We're going to transition to liquids, but we're going to wrap up solids with one little like extra piece of information first. So, what do you think would happen if the solid is dropped into the liquid? So, I have a hypothetical situation here. You have liquid methanol and a block of solid methanol. So, liquid methanol, think of methanol as like rubbing alcohol, but it has less carbons that make up the molecule. Methanol has 1 carbon in it. Your rubbing alcohol is isopropyl, and that has 3 carbons in it. So, anyway, it's just think of it as a rubbing alcohol, okay? So you have liquid rubbing alcohol and solid rubbing alcohol, and you drop this block of solid rubbing alcohol into the liquid. What do you think is going to happen? Will it float, sink, or like hang out in the middle here? Make a prediction and we'll see what happens. Okay, prepare to be amazed here at the animation I have. So we're going to drop the solid methanol in, and we're going to see if we were right just a couple seconds ago. Alright, sank. Okay, very anticlimactic there. And we would expect the solid to sink because the particles are more, like, they're closely packed. They're more dense in a solid than in a liquid. Typically, like we had that on the previous slide, that's typically the case. This will happen for anything where you have a solid and a liquid of the same substance. Okay, so that's key there. Solid methanol, liquid methanol, solid's going to sink. This happens really all the time, with the exception of one main, really important substance. So can you think of what an exception to that is? And you probably could. It's water and ice, right? Which are really the same thing. But if you drop solid water into liquid water, it doesn't sink. It floats, right? So why does that happen? Why is that the case? I have a short clip here that explains that, and that'll lead us into liquids and then eventually into gases. So let's check it out and see what happens.
Bring this glass in here and take a cube and drop it in there. Wow! Now this is water. See the ice floating? Look what happened here. Have you ever seen solid sink to the bottom like that? Looks pretty bizarre, doesn't it?
The liquid on the left is an organic solvent. A frozen cube of it sinks because the solid form is denser than the liquid.
When substances cool, when they get colder, the molecules slow down and they get closer together. They pull in closer together. So the solid is more dense than the liquid. And so the cube should sink in its own liquid. But water doesn't act this way. As it freezes, it becomes less dense. It expands. Let me show you some proof of that. A full bottle of water put in the freezer will break. Why? Well, as water goes from the liquid to the solid, it expands. Now, this is the only substance I can think of that does this.
As a material changes state between solid, liquid, and gas, its density changes. Usually, solid is denser than liquid, and liquid is denser than gas. So why does ice float? Well, the molecules of a solid object are usually tightly packed. That makes the object dense. But ice has an open honeycomb-like structure with lots of room between the water molecules. The density of ice is only 0.917 grams per cubic centimeter. When ice melts, its open structure falls apart, and the water molecules move much closer together.
Okay. So I think that's really interesting and really neat. You can see that when water is a solid, it had a really nice like honeycomb structure, and I can't reverse right now, but the particles were definitely more spread apart, right? And they had that really nice shape and structure to it. And then when it melts and turns into a liquid, we lose that. So if I backed it up a few frames here, you'd be able to see that these particles are further apart, right? And now that when it melts, it loses that structure. They're actually closer together here, so they're more dense right now as a liquid than they would be as a solid. So only substance that does that, part of it has to do with the hydrogen bonding it has and some other things that are a little more in-depth, but I think that's really, really cool and really neat that liquid water is more dense than solid water. That's our one main exception to that, that trend, okay? So that's pretty neat. And here we go. Let's wrap up liquids now that we're thinking of that. So here's my little animation of liquids here. So the particles in a liquid, they move freely over one another in an unorganized pattern. So it's clearly not a lot of organization here. You can see they're kind of moving everywhere. They're definitely not vibrating in place. Like they're not in place at all for a liquid. They're moving definitely faster and over and around one another. We had this already. They do not have a definite shape. They take the shape of their container. And they do have a definite volume, right? That still is the case here. So these don't really expand or contract to fit the size of their container. If you had a little bit of water in a glass, you poured it into a huge bucket, you'd still only have a little bit of water in that bucket, right? That would be a different story with gases. And particles stay in close contact with one another, but usually, there we are again, usually less dense than a solid. We have to say that because of water and our exception to that rule. Okay, so that's our kinetic molecular theory for liquids. And if you look at that animation on the screen or go to that website where you can play around with it, you would see a lot of these patterns and trends. All right, last one, gases. So let's do our kinetic molecular theory for gases. Now we do a whole unit on gases towards the end of the course. We're just going to do a little intro to it right here and see how they move. So you can see the animation up here. It loops after a while. So you can follow one of these red pieces. They're easier to follow. Just follow one of those around the screen there and just kind of see what it does. And you can get our understanding for how gases move in terms of the individual particles. So we know this already. Gas is matter and has mass. Talked about that about 20 minutes ago in this video. Particles have a large distance between them, way more distance between them than other particles do. And in reality, this animation here in this little section of the screen, if the gas particles were really this size, if this is what they truly were, there wouldn't be this many in this little box. They'd be way further apart than that. But that would be like the worst animation ever if you had like one dot in here floating around, right? So they put more in there so you can see how they interact with one another. Small point here, the actual volume of particles is 0 compared to the space that they occupy. So we say gas particles are like infinitely small, okay? I mean, they have to have some size, right? But like in terms of the big picture here, they're like an infinitely small dot particle, okay? Compared to the space that they occupy. So that's interesting. Particles are in constant rapid random motion. Think of a gas particle as like it has a blindfold on, like it has no agenda for where it wants to go. So if you want to act like a gas particle, you would just like stand up, put a blindfold on, and just run around, okay? Smash into stuff, and then just like you run into something or somebody, you just like, okay, go the other way, right? And then you run into something else. But that's what gas particles really do. They're in constant rapid random motion. Their movement kind of depends on temperature, like how fast they're moving, but that's like they never really get tired, okay, unless our temperature gets like really, really, really low, and they move at a slower pace. We'll talk about all that way, way, way later. Pressure is caused by collisions of particles with the wall of the container. Pressure is not really caused by gas particles running into each other, but they're caused by the gas particles hitting the walls of this container. So if you speed up the particles and like hit the container more often and with more force, the pressure would increase. If these particles slow down, like if you decrease the temperature, they would hit the container walls less often and with less force, so the pressure would decrease. So that's what pressure is caused by. And temperature is the average kinetic energy. So kinetic energy is the energy of movement. So on average, how fast are the particles moving? That's what gives you the temperature. We'll talk about some of those finer details a little bit later on as well. Okay, so that's your kinetic molecular theory for gases. Again, we do a whole unit on gases later on, but this is some basic information about them and how it differs from solids and liquids. Okay, let's wrap it up here towards the end of this introductory lesson. You could obviously go from a solid to a liquid to a gas and back. You could even go obviously into a plasma or a Bose-Einstein condensate, but we're going to focus on these. You want to think of solids, liquids, and gases as having a certain amount of energy. Okay, this is pretty easy, but some students tend to mess it up. Solids are they don't move around a lot. The particles don't move around a lot. They vibrate in place, right? So if you think of the kinetic energy of a solid, it's pretty low, right? So those particles are just vibrating and they're not really moving around very quickly. So solids have very low amounts of energy, and gases are always moving, and they're always in that random motion. They have a lot of energy, a very high amount of energy, okay? So as you go from a solid to a liquid to a gas, it is increasing in energy. As you go from a gas to a liquid and back to a solid, you are decreasing in energy, okay? So if you're a solid and you want to turn into a liquid, energy must go into that process. So for ice to melt, you need to put energy into that, so we go to the liquid state. Okay, that's how this is working here. So you're absorbing energy as you go from solid to liquid to a gas, and you are releasing energy, you go from gas, liquid to a solid. So when you put water in the freezer and you want to turn it into solid ice, that liquid water needs to lose energy in order for it to become a solid. All right? So almost all substances can be solids, liquids, or gases. There are a few exceptions. I want to say helium is one of them, where it can't exist in certain states of matter, but for the most part, everything could be solid, liquid, or gas, depending on temperature and pressure and some other information that we'll talk about at a later point in time. That's right here. The phase will depend on the temperature, pressure, and attractive forces. We do a little bit of attractive forces in the discussion there later on in the course, and a lot of it in AP Chem. That's a really interesting component of chemistry and tells us a lot about why certain things are solids, liquids, or gases. It's really cool. So here's our conclusion here. As a substance gains kinetic energy, it will change phase. Lowest amount of energy, Bose-Einstein condensate, all the way up to plasma. All right. As we change phases, we have different names for these things. So you can take a look at what a solid to a liquid and liquid to a solid is called, and then same thing for the rest of these. Let's go through them real quick, because you know most of them, I'm sure. Solid to a liquid, we call that what? Well, we call that melting, right? Liquid to a solid, obviously, is freezing. Usually, everybody knows those. Liquid to a gas, gas to a liquid, we're usually pretty good on these two. Liquid to a gas is evaporation, and gas to a liquid is condensation. And now we get to the interesting ones, I think. Solid to a gas or gas to a solid. So it's skipping the liquid state completely. Some students tend to know what a solid to a gas is called. Solid going straight to a gas is actually called sublimation. Dry ice is an example of this, if you've ever played with that or been exposed to that or seen that. And a gas to a solid, obviously, is the opposite of sublimation, and that is deposition. Okay, so we need to know what those terms are. You probably know 4 out of the 6. The ones that trick students up are the solid to a gas and gas to solid transitions. Okay, so make sure you know what those are called. And to wrap it up here, what is sublimation? Sublimation is a change that skips the liquid state. So here's some examples. Freezer frost is one of them. Iodine crystals, mothballs. You ever have those? Maybe you have like an unwanted animal living under your front porch or something, and you want to get rid of it. Some people throw mothballs underneath their front porch, and they're just solid. Naphthalene, I want to say, is the molecule name for that. And they smell horrible. Then they just eventually go away. Right? They're like bigger pellets, and they eventually turn into smaller pellets, and then no pellet at all. So that's interesting. Here's dry ice, right here. Solid carbon dioxide. So dry ice basically looks like an ice cube, like a foggy ice cube. It's really just carbon dioxide as a solid. So when it goes through sublimation and it turns into a gas, it's the same as the air you breathe out, which is carbon dioxide. So that's really cool to play with. You don't hold it for a long time, though, like a second, because it's so cold that it actually will burn your skin. Not with heat, but with the amount of coldness it has. All right, that takes care of it. That's the whole first introductory lesson here on Introduction to Matter and States of Matter. So hope we found that interesting and informative. And the next lesson is on elements, compounds, mixtures. We're going to focus on those, the differences, take a look at mixtures a little bit more, and just kind of see how all that operates. All right, guys, thanks a lot.